working at Artifact Studio, where I did the UI programming for a tactical game called Space Hulk Tactics. And then I worked for 4 years at Dowino, which is a small, serious game company, where I worked on some VR games and mostly mobile apps. But these last years, I've discovered game jams, which I really love. I've done a lot of game jams in these last years. I think it can almost be called an addiction at this point. I've formed a team that is called the Guilloteam. And together we've done, I think, 10 games in game jams, mostly at Ludum Dare and GMTK, where we got really good scores. How Today's Mushroom, for example, got the 12th place at GMTK last year. And there are a lot of different concepts that we are really proud of, and we hope to turn into commercial games one day. And currently we've started working full-time on a game that is also coming from a jam game that is called Minight Blood Rush. It's a fast-paced roguelite where you play a cute little vampire that faces the cult of the sun. So the idea is that your health is your only resource. So you need to consume some of your health to get upgrades, and the strongest upgrades cost you health over time. However, you can get back some health by eating enemies. So the stronger your build gets, the faster you need to be to get back the health you are losing over time. So I'm going to talk about how I implemented the AI for the enemies in this game. So as you can see, there are quite a lot of different enemies. We have melee enemies that just follow you and try to attack you when you are in range. There are casters that throw projectiles at you. But also more complex behaviors like assassins that hide behind bushes and sometimes teleport behind your back when you try to hit them. So the AI is not actually rocket science, but I needed a way to iterate quickly, especially without having to modify code every time I change a timing of an attack, for example. Because I'm the one who also does the game design for the enemies. But I like to have programming and game design tasks really separate in my mind. So at first I thought I would find a simple system that would already be included in the engine and that would do exactly what I want. But we'll see that it's not actually the case. So I started trying to use the Unity state machine system. That is something that was made originally for animations, but actually the Unity team added features over time that allowed to attach scripts to any state. Which allow to do complex behaviors with it. However, I don't actually use the animation system because I run my own because it is I prefer the animation system is made for 3D skeletons and we only have 2D assets, so it was easier to make my own system. And I don't really like this system because I find the UI really tedious. There's a lot of things to tweak every time you want to add a connection between two nodes. And it becomes really messy when an entity has a lot of states. So the next thing I tried to use is a behavior tree plugin. So the behavior tree is quite an academic system that is used a lot to handle AI in games. It's really powerful because of the tree structure that allows to combine simple behaviors together and to create complex things. So it's exactly the kind of thing I want to do. And there are many plugins in the asset store. However, I didn't find any good free solution, and even the one that are not free that I tried didn't have every feature I wanted, and it's really hard to know whether a plugin has all you need before buying it. So and I don't really trust third-party plugins because every time I used one, it ended up disappearing suddenly, and it's really hard to keep working on a project when a plugin is not updated. So actually, I ended up making my own system. So it's not something I did all at once. It's a piece of tech that I made first for a game called Sensivis, which is a serious game that is supposed to help people understand how people with visual impairment live and the problem they faced in their everyday life. So it's a really linear scenario where you are in an apartment and you do a simple task like checking the time on the clock, trying to read what's on the newspaper. And you can try different things to help you, like having a magnifying glass to read things like that. So the scenario was totally linear, and I made a system to handle that. But I discovered that the system was actually even more powerful than I thought at first. And by adding some non-linear features over time, I ended up with a system that I can use for most things I do. And I refine the implementation all the time. It's getting better and better, and I end up with a system that is only 200 lines of code, and that I can even re-implement every time and tailor for every project. So I really like this system. So the first thing I noticed when trying to implement such a system is that I don't really like building editors, custom editors. I find it really time-consuming, and it's really hard to update it over time when design requirements change. So I prefer trying to only use what is already in the engine, and the Unity Scene Tree system has every kind of feature I would need to make a scenario system. So the basic idea, on the right you have the scenario that I use for Sensivis. So it's just a list of game objects that I call a scenario node, to which I attach what I call behaviors. So it's just mono behaviors that handles simple things, like for example showing a pop-up or displaying a line of text. And all these nodes play one after the other with a condition to go to the next state. So here is a simple implementation of such a node system. So we have I like using delegates. So it's a system.action, which is actually just a delegate. So a node has a list of different delegates that are the main events that are used by the system. And the idea is that it's the same script that is attached to every node, and any behavior can subscribe to these events. So you have the delegate that is triggered when the node is entered, when the node is exited, when it is put asleep or awakened. We'll see later when it happens. There is the update delegate that is called every frame while the node is active, and a condition delegate that I will explain a bit later. So that's what behavior look like. So the implementation is pretty straightforward. So we have a require component. So there has to be a state tree node next to it, so it can be added to a game object. And the first thing it does in the start function is query that state tree node and register things to the delegate. So here we have the most simple behavior possible that just waits for a set amount of time. So it has a duration that is public, so it can be edited in the editor. And in the enter node delegate, it initializes itself, so it resets the timer to 0. And in the update function, it increases the time. And then there is that condition delegate that is actually a delegate that must return Boolean that says the behavior is supposed to return true until it has finished executing its actions. So here it returns true until the time has passed the duration. So with those simple delegates, we can do almost anything we can want, like wait for X seconds, that's what I showed earlier, play an animation, spawn a prefab, show a pop-up, wait for an input, etc. And the idea is that thanks to the exit condition, we can easily combine behavior together. The idea is that we can't exit a node until every behavior within it has finished executing. So it allows to combine absolutely anything together. For example, we have a piece of the melee enemy behavior that is just an attack loop. It's just the sequence of action that makes the enemy follow the player and try to attack it whenever the player is in range. So we have the first node is the follow player. So there are three behaviors. The first that plays the walking animation, which is a simple animation that loops. Then we have a move to target behavior, which handles the movement. It's a simple one. It just goes straight in the direction of the target, which is the player. And then a behavior that handles uses the exit condition to force the system to stay in the node until the player is in range. So we pass to the next node whenever the player is in range, and there we have the prepare attack, which is used to play an animation that shows that the enemy will attack. So we have just a wait behavior that forces the system to stay in the node for a set amount of time that we can tweak for balancing reasons. And it plays an animation that prepares the attack. And after this delay, we play the attack animation and spawn the prefab that shows the VFX of the attack and handle damage properly. So that's all for sequential stuff. So we can play any action in order that we want. However, we have to talk about more complex stuff because most of the behaviors have conditions. There are things that loop. So I added three kind of specific behaviors that I call structural states. So if we watch what happens for the whole behavior of the enemy, there is first an asleep state, that is the character idling until the player enters the room. Then we have a state called the damage handler, which is an interruption. I will talk about in detail later. Then it just launches the attack loop that we saw a bit before. And the idea is that the damage handler detects whenever the player receives damage. And it's like a try-catch in C++ code, for example, where whenever at any point of the execution of the attack loop, the player can receive damage. At this point, we come back to the damage handler, which sends the execution to the hurt state that is below. And at this point, it handles the hurt. It decides what it has to do depending on some things. We can go directly to the second hurt state that handles the animation of the enemy hurt directly, or if the health is too low, the enemy dies. And at this point, we can play the death animation, wait for a moment, play death VX spawn to make the enemy disappear and destroy the enemy. So, as you've seen, there are quite a lot. There are three different kinds of structural states. There is first the loop, that is the most simple one. It just goes in the first child nodes, and plays the sequence, and when it is finished, it can decide whether to go to the next state or play the loop again. Then there is the branch that chooses which of its child nodes to play depending on the condition. So, for example, the hurt state that decides whether the enemy has to die or to play a hurt animation. And finally, the interruption, that is the try-catch system I talked about. So internally, the system has quite a simple stack system. There is a tree root that is the script that handles the scheduling of execution. So it holds the stack that, for example, when we are in the prepare attack state, we have passed by the damage handler and the attack loop, so they are both in the stack. And at every time there is only one node that is active, that is the head of the stack, and the other are put asleep. So that's why we had the asleep and the awake delegates earlier. That's it. And so let's see how we handle loops, for example. So they are also quite simple in implementation. When the node is entered, it just pushes the first of its child node to the stack, and so when it does that, it gets immediately asleep. The first I don't know if I talked about. Yeah, so the basic function, the basic thing that happens when a node is exited, is that we directly go to the sibling node by default, and if there is no sibling, we are at the end of a sequence. Then we come back to the parent node, So actually the implementation of the loop is simple because we just have to push the first child, and it will by itself do the whole sequence and then come back to the loop node. At which point it can there is the awake delegate that is called. At which point we can decide whether we want to push again the first node and do another loop again, or exit the node and continue the execution. For branches, it's also quite straightforward. So this is what you see in the internode delegate. So I showed the implementation of a random branch behavior that just selects one of each child at random and plays it once. So there is only one thing that is different from the loop, is that we don't actually want to keep the default behavior of going to the sibling once the child node is finished, because we want to play only one of them. So I added just an override sibling in the nodes that the branch can set to true to all of its children to force them to come back to it whenever it's finished, instead of playing the whole sequence. And finally, we have interruptions, which is the trickiest feature for a simple reason, is that there are a lot of different ways we want to handle them. I took the example of the damage handling system. As I said, whenever we are, wherever we are in the attack loop, when the enemy receives damage, we want it to get it handled by the damage handler, which will send the execution to the hurt state that will then do the handling. However, there is a question of what we do whenever the execution of this hurt branch is finished. Do we want to come back to the state we were at first before taking the damage? Or do we want to reset the attack loop entirely? And the problem is that we don't really know at the moment when the interruption is sent. Because we can have a system, for example, that prevents an enemy from being interrupted when he gets attacked, and that's a feature we have in our game. So I said it works a bit like try-catch and the exceptions in C++. However, when we catch an exception, we directly thrash everything that was executing when the exception was sent, and that's not always something we want to do. And there is another problem, is that what happens when we are already handling some damage. So the enemy is already in the hurt state, playing the animation. What happens if he gets another damage at this moment? So that's all questions that can make things really complicated. So the solution I found, which is not totally perfect, but it works in most of the case I have, was to when the interruption is received, we don't actually touch anything about the current stack. Everything stays in the state it was before receiving the interruption. Instead, we just push the hurt branch directly over it. It does its execution, and at any point, we can have so we directly push the hurt branch so it does its execution, and if there are new interruption that happens, during this time, they also get simply pushed to the stack, and there is a special behavior that can actually, when it exits, it makes the execution. It throws everything in the stack up to the state that handles the execution. So that way, we don't have to. We only put this special behavior for the case where we really want the enemy to be interrupted. For the other case, we just have to not put that one, and when the hurt interruption is handled, the execution resumes normally. So I don't claim it to be a perfect system. It has many things. As you could see, the implementation of everything I said can be done in around 200 or 300 lines of code. So it's something I really like, because I like when things keep simple. However, some things, like you saw, the interruption, are not so easy to do. But I keep finding simpler ways to do things. It's getting simpler and simpler every time I re-implement it. And the main things I'm not happy about is that it's not really optimized for performance. There are lots of things that happen that are not really performant. That's why I'm currently implementing it with Unity, the data-oriented technical stack. It makes the implementation quite more complex, but I'm really happy with how it's turning out. So that's all I had to talk about. If you want to help me, please wishlist our game, Minight Blood Rush, that is on Steam since a few weeks. Thank you for listening.
You mentioned that when considering behavior trees, there were things that you weren't able to do with it. What were those things?
Actually, it's mostly because they all have really different ways to interact with gameplay code, and I didn't try a lot of them because they all cost quite a lot of money. But the ones I tried, I wasn't really happy with. They involve a blackboard system that I don't find really easy to work with.
I have a simple question. In your team, are you the only one working in this system, or is there also like?
Yeah, I'm the only programmer.
Okay.
Actually, the team is composed of me, the programmer, that also does balancing and game design.
Okay.
A part of the game design, because we work as a team, and all the other are artists.
Okay, so you're the only one doing the AI. Okay,
yeah.
Makes sense.
Yeah, so that might be one of the problems of the system. Is that it can become a bit complex for someone that is for game designer to work with, but I think it can work with a bit of if I explain it a bit how it works. Yes.